Anyway, the next panel, International Mars Robotic Precursors. We do those a lot. International institutions, universities, anywhere on the planet, could have an instrument on one of the robots. And that's how we cooperate already, at least on the non-human spaceflight to Mars part. Now, the next panel will be led by Ellen Stofan, and I am thrilled. I am really tickled pink, because I like all her knowledge. I've always loved listening to her. She's a truly old hand at planetary science and space administration. And since last year, she leads one of my most favorite museums. I mean, the Smithsonian National Air and Space Museum is really awesome, I think. And that's now her responsibility. Of course, she also worked before that at JPL on missions exploring Venus, Earth, Mars, Saturn. And she worked at the long-range plan to sending humans to the Moon and Mars in the next decade and a half. And basically, I think she's more than well informed to lead this panel about international Mars robotics. To Ellen Stofan, please come and introduce your panel.
Come on out. Okay. So our topic is going to be robotic exploration of Mars, but I want to start out, I'm going to let my panelists introduce themselves. So Lori and then Sanjay.
I'm Lori Glaze. I'm the director for the Planetary Science Division at NASA headquarters. Prior to that, I spent about 10 or 11 years at NASA Goddard Space Flight Center working on trying to develop mission concepts for planetary missions.
Hello, I'm Sanjay Vijendran from the European Space Agency. I'm coordinating the Mars sample return activities at ESA. I've been in this role for almost a decade now, so it's something I'm really hoping we can get off the ground soon. Prior to that, I worked on the NASA Phoenix mission to Mars in 2008, and so I've been in Mars exploration for around 15 years now.
For a long time, Lori was my boss, so keep that in mind.
That's true.
So I'd like to pull back to sort of 45,000 feet and talk, before we get into the details of how we're exploring Mars robotically, is to go back just for a minute to the why we're exploring Mars robotically and what robotic exploration has told us and where we're going. So huge question, Lori.
That's a huge question. And, one of the biggest questions we have, of course, when we're trying to answer as scientists is there life beyond Earth? And Mars has been one of the keys to that, because we've always thought where you find water on Earth, we find life. And there's always been hints, or we've thought there have been hints that there could have been water present in Mars's past. And over the last 15 to 20 years, the robotic missions that we've had, orbital missions, and then more recently some of the landed missions through Phoenix and the MSR rovers, we've seen that there really is good evidence that water was present in Mars's past. And so we keep trying to answer that question, I think, trying to better refine our understanding of where the water was, how long did it persist, and there's geologic clues in the surface that can be answered through orbital missions or from the surface, and really trying to understand those water cycles and where life may have been able to grow and perhaps persist at some time in the past. To me, those are the biggest questions that we're really trying to get after.
Sanjay?
Just to add to that, Lori, on general planetology as well, understanding the history of Mars and how Mars was in the past when it was warmer and wetter, and how it became a cold, dry planet, is something that has implications on understanding the future of our planet Earth. So this is another reason why we like to understand Mars from an environment perspective as well.
In both of your minds, what have been sort of the standout, they don't know about this question, so, what has been the sort of standout science discovery of the last 30 years that to you motivates Mars demanding the center of attention that it sort of has?
Well, I think there have been some really key findings, certainly from Phoenix, identifying water ice on the surface of Mars. But then more recently, to me, the one that's really catapulted us to continue our exploration has been the discoveries from Curiosity of these complex organic molecules that have been found on the surface of Mars, that really give us that extra bit of emphasis to try and continue looking for biologic signatures on the surface of Mars.
Sanjay?
Yes, just the same from the European perspective as well. The potential to find evidence of past to present life is the biggest motivator. And coming especially from 1996 announcement by NASA of potential discovery in the Allen Hills meteorites of signs of past life, that was the big spur, I think, that's driven the program on all around the world over the last 20 years heading for Mars. And ESA's now developing the ExoMars rover that's going to be looking for signs of life to be launched next year. So indeed, the life question is the biggest driver for Mars.
And I will say, as somebody who's been involved throughout my career with radar missions, I think certainly the contributions that Marcis and Sherrod have made in terms of understanding that there are large reservoirs of ice relatively near the surface, even in the equatorial latitudes, has been something to me that's been particularly interesting from both the robotic and human exploration. The fact there's these large amounts of accessible water ice, I think, has been extremely exciting. I want to give you both an opportunity to sort of talk about, okay, what is the program of record? Like, what are we doing now? Before we talk about what could be, let's talk about sort of what is. Sanjay, I don't know if you want to go ahead and start. I don't know what order these slides are in.
Sure, I've got some slides, if you can put up the slides from ESA. So I've just got a few slides here to tell you what we're doing at an international level between ESA and NASA on preparing a Mars sample return campaign. Next slide, please. So there's been a lot of work on by multiple space agencies in the international forum, global forum, to develop this global exploration roadmap, which has the horizon goal of sending humans to Mars. So this is a shared objective amongst the many space agencies around the world that are in space exploration. And you'll see on that map that robotic Mars sample return is a step before we go to send humans to Mars to better understand the planet. So what we're working on now is indeed in line with what all the space agencies around the world believe is the pathway towards Mars, with the moon as a stepping stone, but also robotic missions to Mars. Next slide, please. And you can go to the next one. So we've been actively working with NASA for a decade now on looking at how we can do an international Mars sample return campaign together. Prior to that, in the 2000s, and of course on the NASA side, even longer than that, the agencies have been looking at doing Mars sample return on their own. But 10 years ago, it was realized that this was such a big endeavor that it's something that we really need to work on together. So International MSR Campaign was started to be studied with the publishing of the IMARS report in 2008. So in the last few years, last 3 years, in fact, we've been re-energized in our working relationship together with ESA and NASA, looking at how we can do this in the 2020s. Now that Mars 2020 is in development and will be launching next year, and Laurie will talk more about that, and the ESA ExoMars rover is also launching next year. It's time that we look seriously at what we're going to do after that in the 2020s. So the two objectives we've been working towards together is the return of at least 0.5 kilogram of samples from the surface of Mars to be analyzed in Earth laboratories, and at the same time to ensure that we comply fully with all the planetary protection requirements that are required for backward planetary protection to protect the Earth. And this is a key driver for this mission. Next slide, please. So that first step, I won't say too much about it, Laurie will talk about it, is already underway. So we must remember when we talk about Mars sample return, it's about finishing Mars sample return because it's already starting. The next step would be to look at the retrieval missions. And so NASA is looking at the sample return lander mission, which would have a rocket that would launch samples into orbit. And ESA is taking the lead on the Earth return orbiter mission, which would capture the samples in Mars orbit and bring them back to the Earth. Next slide. So this is my last slide, and I just wanted to point out what the connection might be between Mars sample return and humans to Mars. What are the feed forwards that we see? Next slide. So the first aspect is environmental hazards. This is something that we can understand about Mars in a much better way if we have samples returned from the surface of Mars. So the dust, the toxicity of the dust, any possible pathogens in the Martian soil. This is something that we can properly understand with return samples as a feed forward to understanding what our astronauts would face on the surface of Mars, as well as engineering system safety. So how are the equipment on the surface of Mars going to function in the dusty Mars environment is something we can understand better by understanding the dust properties themselves. Next slide. And finally, the important question mentioned many times today, both for the Moon and Mars, is how we can live off the land, in situ resource utilization. So this is something as well that we can understand better through return samples, and maybe not necessarily with the first Mars sample return, but if you think about multiple Mars sample return missions in the future, we can target our returning of samples to understand better the properties of the materials that we would eventually use on the surface of Mars.
Okay, thank you. Great.
Lori.
Okay, thanks. Oh, I get music.
Oh,
I get a
you get
soundtrack.
music. Very nice.
Can we turn off the sound, please? Thank you. Next slide, please. One more, thanks. Right, so this chart here shows our current and future planned missions, robotic missions that NASA's involved with, not just leading, but also partnering with international collaborators. Along the top is a swoosh that shows some of the orbiting missions, including missions that are doing science, still doing a lot of great science at Mars, but also serving as a communications infrastructure. And this includes missions like Mars Odyssey, Mars Express, the European Space Agency Mars Express, the MRO, Mars Reconnaissance Orbiter, MAVEN, which has now been moved down into an orbit to help support the Mars 2020 landing as a communications asset. And then there's also the Indian Space Agency mission up there, Mars Orbiter mission, and then most recently the Trace Gas Orbiter from ESA is also now in orbit doing full science, but also supporting communication relays from the surface. So this is an incredible fleet to not only do science, but to support robotic activities on the surface. And currently on the surface, of course, you heard a lot about InSight this morning, which is doing fantastic science to help us better understand the seismic environment and also the weather on Mars, giving us the highest resolution weather data that we've ever had on the surface of Mars, which is fantastic. And then Curiosity rover, which I'll talk about again in just a moment. Looking forward, you can see also additional missions that we're working, and then also international agencies, including the United Arab Emirates working on their mission, JAXA working on the Mars Moon's Explorers, which will be a sample return from Phobos, and we're collaborating with them on that as well, which will be the first opportunity to bring something back, a sample from the Mars system, and that will be an exciting activity as well. So if we go on to the next slide, just talk a moment about Curiosity. So as I said in the opening, I think this has been an incredible mission to explore the environment within Gale Crater, where we've discovered, it really was an environment that had standing water, and not just any kind of standing water, but standing water that was of a pH level that could have been safe for life as we know it. And so I think that was an incredible discovery, and then also the discovery of the complex organic molecules there is an indicator that there could in fact be the right chemicals, the right building blocks for life on the surface of Mars. So this has been a great mission to really spur us forward and lead us to the next mission. The next slide is the Mars 2020 rover, which, as Sanjay said, is going to launch in July of 2020. This has been also a fantastic international collaboration in order to put this mission together. It looks a lot like Curiosity, and it's intended to. It's intended to be a rebuild of the basic rover, but with an entirely different instrument suite. To not only do science, but this really, as Sanjay indicated, is the first step in sample return. And this mission is, the landing site was chosen over the last few months. It's going to be Jezero Crater, or I think I'm told the correct pronunciation is Jezero Crater, which is an environment where we believe there is an ancient river delta. The kind of environment where on Earth, a river delta, if there's any place where you would find life, it would be in this type of environment. And so it's chosen because it's an ancient river delta that's about 4 billion years old, and we expect to find there, if there were life, we would be able to find it. And we will be taking samples that can come back to Earth where we can analyze them with more advanced analytic capabilities than we are able to bring to the surface of Mars with us. And so this, as I said, the very first step towards Mars sample return, but it doesn't do us any good to collect and cache the samples if we don't bring them back. And so the next step, as Sanjay said, is to bring them back. If I can get the next slide. Sanjay already talked a lot about and gave a very good description of the motivations for the Mars sample return mission. And as he indicated, NASA and ESA have been working very closely on this in kind of a new approach to how to do an international collaboration as far as getting in front of the concept. And a year ago, the two agencies had an agreement to do a joint study of what this mission architecture might look like. And in that agreement, essentially assigned different roles for the two agencies to go off and do studies in a joint fashion to understand just how this could be done together. So this architecture shows a launch that carries, there would actually be two launches, a US launch and an ESA launch that would go at the same time. And they would fly to Mars, and that would include, as Sanjay said, the ESA side includes the Earth Return Orbiter, which would bring the sample back to Earth, but it also includes a fetch rover that would be carried to the surface on the US lander. The US lander also includes the Mars Ascent Vehicle. The fetch lander would go off and collect the samples, bring them back to the lander, to the home base, put them into the sample return capsule, which is put onto the Mars Ascent Vehicle, which goes up and rendezvous with the Earth Return Orbiter, and bring those samples back to Earth. And so the idea is this complete partnership with different elements provided by the two agencies, again, with the orbiter and the fetch rover provided by ESA, and the other elements, the Mars Ascent Vehicle, the lander, and the sample return capsule provided by NASA.
Should add also that the capture system in the Earth entry vehicle on the orbiter is to be provided by NASA. So,
that's correct.
So we have payloads on each of the partner missions.
Exactly. So we carry payloads, and it's a shared partnership all the way around, with clean interfaces and well-defined roles. And I think that helps a lot as well. And trying to get in front, as I said, of the funding processes in both on both continents to try and align our strategies with the type of funding cycles that we all have to deal with. And so one of the important steps that I can say today is that in our current US budget that we got for the proposed budget for 2020 actually includes a line item for Mars sample return, which is a huge gain for us on this side, that we now have the support of the administration to move forward on this activity, and we're very much looking forward to moving it forward.
Now, in the early 2000s, I think it was 2003 or 2005, the US National Academy of Sciences did a report called Safe on Mars that actually said we should do a sample return mission before we ever send humans to Mars. I'm curious, it's now over a decade later from the time that report. That's obviously the path you're going down, but what would you say to an outside entity, perhaps a commercial company or some other organization that said we didn't have sample return before we went to the moon, why do we need sample return before we go to Mars? How would you both respond to that?
I'm going to respond in a way, I feel that, as I said, there is a potential for life on Mars. So there is a difference between Mars and the moon. And we didn't know that, of course, when we first went to the moon, but we know now that the lunar samples are safe from a biologic perspective for humans. But we don't actually know that yet for Mars. And as we're developing the plans for Mars sample return, one of the really big aspects that we're studying very carefully is what are we going to do and how are we going to treat those samples when we bring them back to Earth? How are we going to keep them safe, and how are we going to keep ourselves safe from anything that might be contained in the samples? So I have to say that I do feel like that it seems like a good idea to try and bring those samples back and look at them. I'm not saying that it's absolutely required, but I do think it would be very informative to us as a human race to understand what might be present in those rocks.
Sanjay?
That's a good point, Laurie, about the backward protection. But when we think also about the astronauts that we're sending to Mars, it's an aspect of how much risk do you want to take. So, of course, you can try to go to Mars without understanding Mars to such a great extent, but then you're taking more risks than if you did try to understand better what it was that you're facing when you get there. So I see Mars sample return as contributing to that lowering of the risk of a human mission through a better understanding of the environment by bringing the samples back and analyzing them. So it's a risk perspective.
When you think, since this is the Humans to Mars, what do you think of the missions you have planned in terms of not just answering those big science questions that we talked about earlier, but in terms of making the necessary measurements, getting ready for in situ resource utilization? What are the measurements we're making and or instruments that we're taking, and what are the things we need to do you think, with robotic exploration to really get ready for human exploration? This is both on the way to Mars and on the surface of Mars.
There's a lot of crossover between the science and what's needed for exploration, and we've seen that on the Moon, and we see it on Mars as well. Again, the water is one of the key pieces. It's part of the scientific story, but it's also one of the key things that we're going to need if we're going to be able to implement an in-situ resource utilization. Water is going to be the key resource. So the ability to really localize where water is present, to understand how deep it is beneath the surface, what kind of form it's in, whether it's liquid, whether it's frozen, whether it's contained or tied up in minerals, understanding exactly how we're going to get at that. And I think those are the types of measurements that we need to be making. And certainly, like you mentioned, the surface penetrating radars that can help us, and have already helped us start to localize where water might be present. The missions that we're sending to the surface to help us better understand the types of water that might be present in different places and the types of rocks that we see. I think those are the kind of measurements that we're going to need. Like I said, a lot of crossover between the science and what we need to prepare for humans.
Absolutely, and on top of the scientific understanding and the measurements you would do about the environment that we've talked a lot about, there's also the technologies and the capabilities that you'll want to use robotic precursor missions to develop, to prove out. And we talk about going to the Moon to prepare human exploration, using that as a proving ground. These robotic missions to the surface of Mars are a proving ground as well for new capabilities, like landing large payloads, for example, new power systems that we might need, dust cleaning off our solar panels, accessing the subsurface. These are all capabilities that we'll want to develop before we send humans to Mars, so that we are sure that they're going to work when they get there. So we can use robotic missions as well for these kinds of capability building steps.
And are there actual planned demonstrations that will take place, say, within the next decade that sort of are definitely feed forward into that technologies?
So Mars 2020 is carrying at least one example of that, the MOXIE experiment, which will be I'll probably get the acronym wrong, someone will shoot me. It's the Oxygen Exchange Experiment, which is being developed by the Human Exploration Mission Directorate to actually demonstrate the ability to convert the CO2 to oxygen.
CO2,
Yes.
Yeah.
So we are doing some experiments along those lines, but certainly I think more of that is needed. Through the Lunar programs that we're working right now for the commercial lunar payload services that I think was mentioned a little earlier this morning, we're developing a lot of technologies that could feed forward to Mars, that are also trying to develop the capabilities that we're going to need to make use of and to live off and be sustained on the surface of either the Moon or Mars. So we are working on a variety of those and do technology demonstration through that, hopefully rapid access to the surface of the Moon.
And what about ExoMars? Are there feed-forward things on ExoMars?
So for ExoMars, it's really a science mission. So it's about searching for life. So the feed-forward is understanding whether life exists or has existed, and how that might impact whether we send humans or not, or in fact might provide further imperative to send humans sooner than later if we show that there's something there to be found. But from the ESA perspective, we've been so focused on Mars sample return as our long-term objective of our Robotic Mars program that we haven't spent a lot of time yet looking at what we would do after Mars sample return. But if this goes ahead at the end of the year, as we hope it would, from next year onwards, we would be starting to look at the kinds of missions we would do after Mars sample return in the early 2030s that would support eventual human exploration. So the kinds of things just mentioned, testing in situ resource utilization technologies, for example, is something I can see that would start to become important as we look at robotic precursors in support of human missions.
And obviously, as you talked about, the whole issue of landing large payloads on the surface is something that's really critical, and that's something that will be tested. And of course, just the issue of ascent itself from the Mars surface, which is obviously something we've never done before.
Exactly, and so with the sample return architecture we're talking about, we'll demonstrate that for the first time, being able to actually launch from the surface of Mars and dock in orbit with the return orbiter. So those are some new things that haven't been done at Mars before.
You know, when I go out and give talks, a lot of the times I do, you know, I still do get the question of this, do we really need to send humans to Mars versus just doing everything with robots? And I try to turn the question around, and I'll turn it around for you. It's not so much humans versus robots, it's humans with robots. And so can you talk a little bit about looking forward? You know, okay, let's fast forward 20 years from now, we've got humans on Mars. How are we still using robotic exploration to further science and exploration on Mars? Sanjay, I'll give that to you first.
Okay, thanks, Anne. I think we use robots especially to do mundane tasks. And I think once we send humans to Mars, there will be tasks as we start to set up infrastructure where robots can be automated to do things instead of humans, because there'll be a few humans and their time will be has to be spent very usefully, and robots will be needed to set up infrastructure, to build things, to maintain things. So these are areas where we can really benefit with the partnership between humans and robots. And this aspect of using robotics will also drive autonomy that will be needed in order to allow these robots to function in an autonomous manner as well.
Yeah, and I think it's a great question. I never think of, is it humans versus robotic exploration. I think whenever we do send humans, it will absolutely be a joint exploration between humans and robotics. Just thinking from my background, trying to study geologic things, as a geologist, you would want to go out and explore. Once we're there on the surface of Mars, we're not just going to sit in the habitat, I hope we get out and move around a little bit. And if we had things like rovers that can go out and explore before, so to help us find our way, or perhaps even, we're going to have a helicopter that's going to fly with Mars 2020 and demonstrate aerial flight in the Mars atmosphere, which is just a phenomenal demonstration in such a low density type atmosphere. But if we have that capability, you can imagine a small drone that could go out and do sorties and do reconnaissance and help identify where you want to go to help maximize your efficiency and your effectiveness. As an explorer, I think those are the other types of things where the robotics are going to be key to maximizing our presence while we're on the surface.
Now, obviously, when we think about exploration or how we explore on the surface of this planet, we incredibly rely on things like, for example, GPS, the comm satellites that help us communicate. So when you think of that infrastructure piece, also, I'm curious, sort of, again, a little bit forward-looking, but how is that going to be needed in order to have any kind of sustained presence on the surface of Mars?
I think you heard this morning that Administrator Bridenstine said that there is an expectation that when we go to Mars, there will be some type of a permanent fixture in orbit, similar to what he's envisioning for the Gateway. But I think in addition to that, we've already shown that our network of orbiting spacecraft provide a great, not just the GPS, but also the communications network that allows us to constantly have access and communication to any of the assets on the surface. So I think certainly, NASA's thinking forward as far as what that support capability is going to be there for humans on the surface. And from a robotics standpoint, from the science perspective, trying to continue the steady stream of orbiting missions that provide that continued infrastructure. But internationally, that's not just a NASA endeavor. I think that's as you saw from the chart, it's becoming more and more an international endeavor.
Absolutely. I think there's a lot of benefit to be taken by the fact that many different countries are sending spacecraft to the same place. And if we start being more forward-looking, we ought to think about how these spacecraft could embark small payloads like communication payloads, which can interoperate with the other spacecraft so that you can take benefit of this relay network as we're doing already with Mars. I think this will happen with the Moon as well, and we start to see interplanetary networks being formed and common standards being produced so that everyone can take benefit of each other's resources for their own benefit.
You mentioned autonomy earlier, and to me that's something in the robotic spacecraft world that's becoming increasingly important. But I think that feed forward to human exploration is really critical when you consider the distance and light time travel, the fact you can't really have Houston, we have a problem, and expect a response anytime soon. So can you talk about how the importance of autonomy and how we're developing exploration?
So when we talk about robotics autonomy and for the roles that the robots are doing, there are many things which, indeed, there cannot be human oversight constantly over that. And the quicker robots themselves can solve problems, the less time investment there needs to be from their human counterparts in there. And there's a lot of spin-in from commercial interest in AI, artificial intelligence, and autonomy on use on the Earth that we can use in space as well. And we're starting to look at how we can spin in these huge investments that are going into autonomy for Earth users. But there's also ways that we can spin out that from the space industry. But the sheer number of robotic elements that will eventually be needed to support a human presence, I think will necessitate the use of high levels of autonomy, because we just cannot expect astronauts to be holding the hands of our robots in the way, and with the light time difference, indeed. It will have to be the on-site human beings who are in charge of the robotics.
Absolutely, and there is a lot of investment already into a lot of these autonomous systems. I mean, even, again, just kind of going back to the rover systems that we have on the surface now, we've seen progress from the MUR rovers to the Curiosity rover in the level of autonomy and the quickness at which it can move without interaction from Earth, and then moving to the Mars 2020 rover that's coming along. There's going to be even hopefully, as developed, even more advanced autonomy for that rover, whereas we typically had to take images and step back and examine them and then move a few inches, and then it's just been a little bit of a creep at a time. And the intent as we go forward is to develop the capabilities that we're investing in that allow us to say, we're here, we want to be over there, and allow the rover to autonomously navigate from one spot to another. It's those types of autonomous systems that I think are going to be incredibly valuable.
Now, as we move forward, obviously, we're hearing a lot about the cooperation that's taking place around the Mars sample return architecture. And I'm curious if you could both talk a little bit about the levels of overall international cooperation. Is it working? Are there ways we can do better? Where are there gaps? And maybe how we cooperate internationally?
Do you want to go first?
Please.
I would say that certainly right now, around Mars, but also in planetary science in general, there's a tremendous amount of international interest and a lot of collaboration going on. And I'd say that, by and large, those collaborations are working very well, and that we have a lot of great discussions and a lot of new, probably more projects and more activities and missions than we can ever possibly fund, each of the various agencies even working together. But the biggest challenges that we have, I think, and I alluded to this a little bit earlier, is trying to get our budget cycles in sync. And that tends to be one of the forces that works against us in trying to move forward and really to get things confirmed, to move forward, and then to keep them moving ahead with continued budget constraints from the various agencies and various host countries. So I think, as again, the Mars sample return that we're working on now with ESA is an attempt to try and change that paradigm a little bit and get in front of the funding process to get both agencies moving in the same direction in parallel. And we'll see how effective that is. But in my mind, that's one of the biggest challenges that we have to trying to do the international work.
Yes, and I think we've got to the point in science and exploration in general that the kinds of missions that we want to do to answer the big questions have become so big and expensive that international cooperation is is a necessity in many cases in order to pool resources. Now, of course, international cooperation comes with its own risks and challenges, but it also brings a whole lot of opportunity with it. And just like ESA was founded on the belief that if we work together as a group of nations, we can achieve more than a single nation. I think this is becoming quite apparent in our space endeavors now between agencies, between countries. But it's also important to choose your partners well. And I think one of the things that we've learned through the Mars Sample Return Corporation, that the last 10 years of ESA's investments in technology development and studies, but also in flight missions like ExoMars TGO that's flying around Mars, develops our capability and credibility towards an international partner when we start discussions about working together, especially when you do something as big and important as Mars Sample Return, and a partner is playing such a critical role which can't easily be replaced by the other partner if it doesn't work out. Then the credibility of that partner to deliver the result becomes an important factor. So if it's 5% of an overall mission, it's less important than if it's 35% of the collaboration. And so I think it's important, and we're trying to do this on the ESA side, is to do these early technology developments, to do some of your own flight missions to demonstrate the capabilities on your side before you start discussing the next thing you want to do internationally with partners, because you can bring that heritage and that evidence that this is going to go smoothly and you can deliver on your side of the bargain.
Now, we were, unfortunately, we were supposed to have a representative here from the United Arab Emirates Space Agency, and they had to cancel at the last minute, but you've already given a great shout out to them. Obviously, as you mentioned, India coming up. How do we make sure there's room for everyone and make sure everybody has a role? I'm curious in that aspect of the international. How do we make sure now that the playing field is widening, which I think is a great thing? How do we broaden the opening?
It's a great question, and as Sanjay said, part of what the efforts have gone on within ESA is to really develop their capabilities to demonstrate their strengths, and I think that's what we're seeing now with UAE and with ISRO, starting to really demonstrate their capabilities. ISRO with their first mission, successfully on orbit at Mars and doing science, and working now on the second one. We want to try and continue having conversations and working together to help leverage their capabilities and bring their expertise along so that we have more international partners to work with. As Sanjay says, these endeavors are big and they're going to require a lot of international work. So trying to keep those communication lines open and provide the collaborations where they make sense.
Timing can also be important in this, in the sense that if you have perhaps too many players at the early stage of formulating architecture of how to do something, you can spend a lot of time in that period, as everyone has a different opinion about that. And sometimes it's more efficient if one or two major players efficiently come together on what such an architecture should be, and then open things up to niche roles that others could join in to take once the overall backbone is fixed. So how and when you bring in partners and internationalize something is I think depends on a case-by-case basis on what kind of mission you're trying to do.
Now, a last question before we open it up to the audience for questions. I was on a panel earlier this morning talking about STEM, getting kids excited. Can you talk just a little bit about how your missions to Mars, your robotic missions, how do you look to those to leverage that excitement with the next generation of Mars explorers?
Good question. I'm going to cite the example just recently when we landed InSight on Mars, and I thought this was a really incredible event that actually touched not just, and it touched students around the world, but it's touched everyone, and not just your normal audiences of people that are watching the evening news. And part of what the strategy that was taken during that InSight landing was to invite, and this is kind of a different approach, but invited people into that event who were from all walks of life, doing all kinds of different activities, not your normal types of STEM activities, invited them in to tweet and to share their experiences worldwide. And that activity actually, I think, touched an enormous number of people that an audience that we don't normally reach, including students and younger generation of individuals who may not even realize that these are activities that are going on and possibilities that are out there. So in addition to the more traditional types of outreach activities, which we have a lot of those activities going on, but I'm thinking particularly about our specific Mars robotic missions and how we can use those to help reach a broader audience, in particular trying to inspire next generation scientists and engineers. I thought that was one example that was particularly effective, more so than other things I've seen in the past.
I think in the Mars Exploration program, in some ways, we have an easy job with selling our program to the public. It practically sells itself in many ways. People like drama, and this is why EDL for Mars programs has always been a success with the public, and NASA has quite rightly milked that for everything it's worth. But looking at what we're doing now in Mars sample return, I think we have a fantastic opportunity to engage the public. And why do I say this? Is because inherently the architecture, as Laurie has described, we're flying to Mars, 2 launches, a spacecraft lands, it deploys a small rover, it has to find a piece of treasure on another planet. It has to do this in a short period of time because we have to do it before the winter sets in, otherwise the rover is going to get caught in dust storms and die, so there's a time limit to do that. It has to bring it back to the lander, then it launches it into Mars orbit, and then this little ball has to be found by another vehicle, lost in space, and it has to be found and rendezvoused with, also under time pressure, otherwise we'll miss our ride back. And then we bring it back to the Earth, and then it crashes into the ground. So the many different phases of Mars sample return, each of them are actually quite easily understandable and relatable to people, I find. And as a whole, the fact that most of this happens over a fairly short period, about a year, the surface mission has to complete. That's the kind of time frame that the general public can sort of relate to. And there's so many key points that can be put out there as the next thing that we're working to, the next bit of drama that we have to solve. And so I think we have a great opportunity here to engage with people, young people, and the public during the mission itself. And ultimately, it's anyone with kids knows that kids love to go and pick up rocks and bring them home, right, in their pockets. And we're just big kids picking up rocks from a different planet.
So questions from the audience, and there are microphones in both the aisles, so if you want to come forward. And Clive is running to the microphone.
I'm running to the bathroom.
Oh, Clive, now you have to answer a question.
But I can ask my question from there with this microphone. So. All right, everybody's awake now. So listening to Mars sample return, and as a young lad back in the 90s, was involved with Mars sample return by 2005. Wrote papers on it, was thoroughly excited. It was great, and here we are, 2019, talking about Mars sample return. The thing that I was always worried about and still worried about, planetary protection. Forward and backward planetary protection, especially if we're going to impact the sample return canister with a bit of litho braking back on Earth. How are you addressing forward and backward planetary protection in your Mars sample return architecture?
So there's a lot of work going on right now. There's a Mars sample return science planning group that's doing an enormous amount of work thinking about both directions, but in particular about the rocks that hit the surface and how we're going to pick those up and what we're going to do with them and how we're going to make sure that they're safe before we actually open the canisters and start doing the work. And then once we've done that, ensure that everyone remains safe. So there is actually a working group that's thinking about these questions. They've already had 2 meetings, and I think there's a 3rd one coming up maybe this summer, still thinking about those questions. I mean, it's an important question, and so there's a lot of thought going into that now, and how we're going to, what type of facilities are we going to need in order to hold those samples until they're ready to be declared safe, and then how they get transferred into a kind of a more traditional like curation facility if that's a possibility. So there's a lot of thought going into that at this point. That's still kind of in the beginning stages of planning.
Yeah, but the humans to Mars, we're going to be the dirty things that go to
That's
Mars.
true. So that's the forward. Yeah.
So I'm just lessons learned from this is going to inform the human aspect, and then.
So there's actually a meeting going on this week in Houston at the end of the week for planetary protection for humans. Humans to Mars, I believe. So that's going on at the end of this week. So hopefully we'll get some good information out of that.
Hopefully.
And see
Thank you.
what they have to say.
Yes, Doug Cook from Aquila-Mission.Space. You've addressed some of the comparisons between using robotic exploration of Mars and putting human boots on Mars and working with humans and robots together. I've met planetary scientists who are working deeper in the solar system who are vehemently against humans in space, I think because it competes for their funding. From the standpoint of the NASA's Planetary Science Division, and you're working both sides of the fence, I just wanted your perspective on that, robots in deep space versus humans in deep space.
I think there's a balance there, right? I think there's a lot that we can do with the robotic exploration. And you can do a lot of the groundwork and do a lot of the understanding and characterizing the environment and really defining and understanding where you would want to go to optimize. So when you do send humans, that you're sending them to the place where you're going to get the most return for what you're going for, whatever your objectives are. And then when you do send humans, there's a lot you can do that you can't do with the robotics. And that is, again, kind of in real time. We have the most incredible computers in our brains and our eyes that we have yet to really duplicate and replicate with robotic systems. So the ability to scan across and integrate all of the information and make decisions quickly is something that only humans can do. And so that companionship between the humans and a robotic working together in that environment, I think is going to take us to the next step of understanding of those planetary systems going to Mars or beyond. So in my mind, the robotics are the precursors that help us better define and allow us to have those efficient human missions as follow-ons.
Yeah, and I think if you add on to that, I mean, you're talking to Lori and I are both field geologists, so right away we're only going to give you one answer, but you need a field geologist on the surface. But if you consider the question that we're trying to ask, which is, did life evolve on Mars? But that's not the end of the question. If so, to what extent, how widespread? And finding life, okay, check mark, is really not what you're after. You really want to know then to what extent did life evolve? And that doesn't take one sample. It takes hundreds of samples, and that takes boots on the ground.
And I think that the value of human boots on the ground is underscored with what was accomplished on Apollo in hours and days.
Absolutely.
Compared to what robots have fantastically accomplished on Mars, but over a much longer period of time.
Very good point. Thank you.
Yeah, hi, Dave Murrow from Lockheed Martin. So we think about landing on Mars too, and we are chomping at the bit to help with Mars sample return. What can we do, and what are your thoughts about how you plan to engage with industry on both sides of the ocean?
Okay. Well, I can't speak for Lockheed Martin from the ESA perspective, but as you may know, on ESA conducts all of its work through industrial contracts with European industry. So we very much will be relying on our industry to produce the hardware to support us in Mars sample return.
Fantastic.
And from the NASA perspective, we rely very heavily, as you well know, on all of our industrial partners to do the planetary exploration, and Mars sample return will be no different. And it's a little early to say exactly what that's going to look like, but I can say that there will probably be more information on that coming within the next many months.
Super. Thanks. We look forward to that.
Yeah, but you do.
Last question.
Maybe I missed it, but aren't you planning any kind of robotic precursor missions to the moon to support the 2024 mission, and then especially for the 2028 mission to
Yes.
establish a base on the moon, which then could be transferred technology-wise to Mars later?
So thank you for bringing that up. And I did mention the commercial lunar payload services activity that we have going on, which is to buy, and Administrator Bridenstine talked about it earlier as well, where we buy services from commercial entities to fly our payloads. And we actually have our first task order out right now. We expect to make an award fairly soon to carry some of our early payloads, which can include technology demonstrations to show how, again, drilling, in situ resource utilization, radiation experiments, all those types of things on the commercial payloads. In addition to that, we're also hoping to develop capabilities within the Science Mission Directorate to bring bigger payloads, landers that can carry rovers that can move around, survive the night. And so those will also be robotic missions in precursors prior to human landing on the moon.
Yeah, thank you. I'm really addressing developing the precursor missions for establishing infrastructure so the astronauts can live in some habitat or someplace, and establishing that before they land on the moon, and then they use that same process for Mars. But doing science is great, but living and getting established capability is another thing.
So again, as the administrator said this morning, that's the intent, is to be able to get that infrastructure there at some point. The 2024, I believe, will be a landing, and then working towards building, as we go forward from there, that infrastructure that allows sustainability on the surface.
Thank you all very much, and thank you to both Lori and Sanjay. This is an excellent panel. Thank you.
Thank you.
Thank you.